Imagine a place where drugs treat tumors and patients experience fewer side effects from traditional chemotherapy. A place where scientists unravel genes to cure diseases. A place where we learn how to make bones and muscles grow stronger as we age. Satellites refuel in orbit, saving companies billions of dollars. Robots perform dangerous tasks. Scientists discover the mysteries of dark matter, leading to new technologies that change the world. We monitor and manage Earth's precious resources and take advantage of those resources in space to explore farther away from home, where a new commercial marketplace thrives, where people from many nations work together peacefully for the good of all humanity. This place is humanity's home in space and the springboard for future journeys into deep space, a place where we're living off the Earth, working for the Earth. So look up, marvel at the third brightest object in our sky, the International Space Station. We're working off the Earth, for the Earth.
Good morning, everybody. Welcome to our Destination Station ISS Technology Forum. We're here at the Marshall Space Flight Center in Huntsville, Alabama. It's my first time in Alabama, so I'm excited. This is new for me. This is the second destination station that we've done, so thanks so much for joining us here today. So the International Space Station, the first piece launched in 1998. Humans have been on board since the year 2000. So something I always like to point out, there are probably people in this room who, as long as they have been alive, humans have been living and working in space. We are truly a spacefaring species. That blows my mind every time I just think about it. So let that soak in for a minute, and then we're going to continue on. The International Space Station, it's this platform for unparalleled science research and technology development. Technology is what we're going to focus on today. And whenever we think of space flight, we think about the technologies that power it. There's a 300-foot beacon of technology standing right outside this building. So it's not easy to forget about that when we're thinking about space flight. I'm joined by some of the men and women who are behind a lot of the great projects taking place right now in space. And they're going to be able to give some fantastic insight, take some questions from myself and more of you. We're also going to be taking questions on social media. But real quick, joining me today, I have Jeff Sheehy, who's the Senior Technologist from our Space Technology Mission Directorate, all the way down from headquarters, I guess. So thanks for making the trip, Jeff. I have Robin Gatens, and I have to read these titles because in true NASA fashion, we have some pretty fantastic titles too. And Robin is the System and Technology Demonstration Manager from NASA headquarters in the ISS division. Next to her, Jose Benavides, the Chief Engineer of the Spheres Project. And we have Richard Reinhardt, the Principal Investigator for the SCAN testbed, all the way down from NASA's Glenn Research Center in Cleveland. And all the way in the end there, Nikki Werkheiser, who is the Project Manager for NASA's 3D Printing and Zero-G right here at Marshall. So like I said, I'll start off with a couple of questions, and I want to get questions from everyone here joining us in the audience. We'll take some questions from social media. If you're following online, you can tweet your questions with the hashtag AskNASA, and we'll be able to direct it to our expert panelists here. So first, though, if we're going to talk about the International Space Station, it would be best to hear from somebody on board the International Space Station. So in space right now, NASA astronaut Reid Wiseman prepared a little message for us. So why don't we hear from Reid real quick?
Greetings from the International Space Station. I'm Expedition 41 Flight Engineer Reid Wiseman of NASA. Living on this amazing laboratory has taught me how much we need to learn before we can travel to an asteroid or Mars. Not only does the human body operate differently, so does almost everything else, including the technologies to help humans survive in space. The station is the only place where we can test these critical technologies in the environment where these systems will operate. We're testing communication systems, learning how to control robots in space, and using 3D printing to build tools. I hope today's Destination Station ISS Technology Forum inspires you to test a new technology that benefits space travel and the citizens of Earth. All the best for me and my crewmates on the International Space Station. So long.
And I know we all wish we could do that right now. At least I know I do. Okay, so we'll go ahead and get started. Again, I'll ask a couple of questions, and then I'm putting it on you guys. I'm coming to the audience, and you're going to come up with some really great stuff for these guys up here so they don't have to listen to me talk the entire time. So Jeff, you're first up. So you work in the Office of Space Technology, and if you haven't caught on yet, you're going to hear the word technology a lot today. That is the focus. Can you explain why the space station is such an ideal facility to be testing these new technologies that are going to take us even farther out?
Sure. Well, thanks. It's great to be here. Great to be in Huntsville. I spent several years at the Marshal Space Flight Center. I'm kind of on loan from there to headquarters. My bosses here got tired of me and said, why don't you go to headquarters for a while? But the space station's relatively close. It's only a couple hundred miles away, and I came down from DC yesterday. That's 700 miles away, and so it's fairly close by. And certainly when you compare it with going to an asteroid, going to Mars, it's very, very close by. It's like going to your next door neighbor compared to going to DC. And so it obviously takes a rocket trip to get there, and you got to accelerate yourself to 17,500 miles an hour and miles a second, and you have to catch miles an hour, and you have to catch up with that thing and rendezvous with it and dock and climb aboard. But relatively, compared to going to deep space, it's close by. So we can get people there, we can get equipment there, we can take experiments like those that are being overseen by my colleagues here on the panel to the space station and test out the technologies in the microgravity environment. That's the one thing we have a really hard time recreating on Earth. We can build big vacuum chambers and use pumps to take the atmosphere out of those chambers, and so we can simulate the lack of atmosphere in space. We can heat things up, we can cool things down. But what we can't do for more than 30 seconds on an airplane flight that goes over a big steep parabola and puts you in free fall briefly, what we can't do is recreate the microgravity environment. And as the astronaut mentioned, so many of the things we do on Earth, all of our manufacturing process, all of our growth processes in our body, maintenance processes, they depend on gravity. We grew up in a gravity environment and we evolved that way. And so when you are without the influence of gravity, the way you make things and the way the processes go on inside your body change. And so to study that and to study the effects of that, and if we think about going to deep space and trips that are going to last many months, maybe a year and a half or that kind of time frame, we need to look at the long-term effects of these changes. And so the space station being relatively close, being relatively easy to access compared to going to Mars, gives us the opportunity. And so it's an ideal laboratory for that kind of technology development and demonstration.
Right, and a technology I know very near and dear to the hearts of a lot of the astronauts because it keeps them alive, and it's called ECLSS, and this is the other thing. You guys might hear a lot of acronyms. We're going to try to minimize that, but we will also try to explain every single one. So Robin, start off, tell us about ECLSS, what does it stand for, and how are the technologies that comprise ECLSS so important, not only for the space station, but when we start heading towards Mars?
So ECLSS stands for Environmental Control and Life Support Systems. And basically, it's all the machines that keep the crew alive inside a closed spacecraft. So here on Earth, we recycle the atmosphere through plants and our water through oceans and evaporation. We can't do that in a closed spacecraft, so we need machines to do that. So ECLSS recycles, takes the carbon dioxide out of the air and puts oxygen back in the air for the crew to breathe, keeps the atmosphere comfortable for the crew, removes contaminants, and then we recycle all the water, including urine, sweat. We've had our regenerative ECLSS system, some of the parts which were built right here at the Marshall Space Flight Center, on board the space station since 2009. And that's the primary reason we were able to go from 3 crew to 6 crew, because recycling the water enabled us to support more people on the station versus having to keep bringing up water from the Earth, and enable us to do all the great research that we're able to do with more astronauts on the space station. So it's a really important system that the crew depends on, and will be even more important as we go further away from Earth.
And you guys always test the system here on the ground before you make the astronauts do it, right? You're the brave men and women turning yesterday's coffee into tomorrow's coffee.
We did. I have drank the water, and it's perfectly fine. It's actually cleaner than your tap water.
All right, well, next up, Jose, and you have a project very near and dear to my heart, because anyone who's ever seen Star Wars, the original Star Wars, will instantly recognize the Spheres project. Spheres it's a fascinating technology demonstration happening on board the station. Why don't you just tell us a little bit about, what and there are many iterations of Spheres. Why don't you just tell us a little bit about what that project's been doing? It's been on board for years too, so it's...
the Spheres is small satellites operate inside the space station, originally designed as a satellite-type platform for studying those kinds of technologies where we're looking at automated docking, formation flight, guidance, navigation, control type algorithms, where we're learning how to control satellites in a failure-tolerant environment. And that's where we can really take advantage of the unique environment of a research lab in microgravity on the space station.
And just like I said, there's a bunch of different kinds. What are just some of the different, so aside from just, formation flying, things like that, there's a lot of really cool electromagnetic technologies that you guys are testing out right now.
Originally developed to study these kinds of control algorithms that's run its course, but we've had additional investigations take place that attach new hardware to the Spheres to study all kinds of things, from fluid movement, fuels in microgravity environments. You can imagine that takes place in rockets. Vision-based for navigation using cameras to know where you are in your environment, as well as electromagnetic formation flight using these big ring that generate magnetic fields to actuate against each other, as well as smartphones that are attaching to the Spheres to turn these Spheres into more robotic type applications that can assist the astronaut. So all kinds of different investigations from investigators from around the country utilize the Spheres as a platform to study all these different technologies that we're going to need for long duration space flight.
All right, well, and again, two more from me, and then I'm going to start looking for questions. So we're going to have microphones out there in the audience. If you have a question, you just need to raise your hand, wait for the microphone, and then we'll be able to hear it. So my next one, down to you, Rich. Communications, obviously a huge thing, not only in the day-to-day operations of the station, but when we start heading to Mars, it's a much bigger challenge than what we have to deal with right now. You start talking about major communication delays. So the scan test bed, the project that you're working on, how is that helping to change how we're going to be transmitting data, across the solar system eventually?
Sure. So SCAN is another one of these NASA acronyms. SCAN stands for Space Communications and Navigation. It's an experimental communication system installed on the truss of International Space Station. And it's comprised of 3 software-defined radios, or SDRs, you might hear me say. That's the acronym for software-defined radio. But what's different about these radios compared to today's radios that perform one function or one set of functions for the life of the mission. You turn the radio on, it performs that set of functions for the life of the mission, nothing happens to it. With a software-defined radio, we define many of the functions that produce signals that transmit from the antenna or functions that occur to the received signal, all in software. And it's software that runs on processors, much like your computers, or on specialized hardware. But all these functions, in the group of functions and the group of software I might refer to as a waveform. But all these waveforms, because they're in software, are reconfigurable on orbit once the hardware is launched into space, which is just a brand new capability that missions will have available to them. So to put this in context, I'll give 2 examples. The first is I'm going to launch a mission to low Earth orbit. I have no intention of reconfiguring my radio. I have no intention of changing my software, but I get on orbit and I find I have an interference problem. Maybe an instrument's changed or the communication system has a problem. I can correct or change my software to get out of the way of that interferer. Maybe I can save the mission, maybe I can increase the data return, maybe I can help solve the problem by changing that software. So it's great for risk mitigation and problem solving. On the other side, say we're going out to Mars and I need a particular waveform, a particular set of functions for that cruise phase, because it's going to take me 6 to 12 months to get there. And then once I get there, I'll do my operational waveform. Well, in this case, I have to carry a box. If I use a legacy radio or today's radio, one box to do that easy waveform, that cruise phase waveform and maybe a different box for my operational waveform. With a software-defined radio, I can program my radio to do my cruise waveform, and then when I get on station, I can reconfigure that software to do my operational waveform. Now maybe I can reduce the number of boxes in my spacecraft, maybe save cost or money there, but then I can reconfigure, and that'll give me the capability that I need on orbit. So there I intentionally changed my software. And also, because it's 6 to 12 months to get on orbit, I don't need my operational waveform for 6 to 12 months. So I have that much longer to develop that software.
So a lot more flexibility, and again, one of the running themes anytime we're going to be heading out to Mars is you got to be flexible, you got to be able to adapt, because we've never sent humans to Mars yet, and we're going to need to be ready for any possible situation. So my last one for right now, all the way down to you, Nikki, and you're involved in something that, I mean, not only in space, it's a very huge technology right now just down here on the ground, and it's 3D printing. So we're taking it into microgravity now. What is 3D printing going to offer, not only the station itself, but future missions into deep space?
Absolutely, and that's a great question. So we all know 3D printing has actually been around for quite some time on the ground through rapid prototyping and other technologies, and it's rapidly evolving on the ground as well. And at NASA, we're taking those current and evolving technologies and adapting them to microgravity. Just like we talked about here, Reed and several folks here, Space Station is the only platform available where we can actually test this fully. So the first 3D printer that we just launched last month, yay, on SpaceX 4, it's on orbit now. We're getting geared up to do our first print. It is a technology demonstration. And that's a critical point because we've done all the foundational work we can do on the ground. We have ground tested. We have, between NASA and the company Made in Space, we have flown over 500 parabolas on the aptly and affectionately called Vomit Comet. And so we have a lot of really good foundational data, and all of this points to the fact, and it appears that the parts we print in microgravity are analogous to those that we print on the ground. There are even some areas where we feel like microgravity will help. We see things like overhang and sag when we print on the ground. But the exciting part of this is a technology demonstration, and it's the unknown unknowns of microgravity where we learn the most. And Space Station is the only platform in the universe that can reveal those. So the first actual fully 3D printed part in microgravity can only take place at this day and time on Space Station. And obviously, this is a technology, just like all of my colleagues discussed with their technologies here, every one of them require hardware. And hardware, we need to be able to evolve on long-term missions. Things break, things get lost. So the capability to be able to make what you need when you need it on demand in space is incredibly exciting, but it is also a fundamental enabler to ensuring that we have sustainability in an affordable and realistic way for exploration missions to places like Mars. So we are extremely excited to have the space station as the test bed for this technology, to be able to adapt to Space Station as well as for any exploration mission.
Okay. And now it's your guys' turn. So if you have a question, raise your hand. We'll run a microphone over to you. Again, wait until you get the microphone. Who's my first victim? Who wants to go first? Right up here.
With the ISS system, you said that it recycles water, but since your body takes in water, how often would you still need to bring up water for it to replenish the system, since you're losing some every time it recycles? And how would you take that up, and how much would you take up?
That's a good question. Am I on?
There you go.
Okay. Right now on Space Station, we can recycle about 80% of our urine and all of the rest of the water, all the sweat water. So altogether, about 90% of the water gets recycled on Space Station with the technology that we currently have. What's left over that we can't recover is a really icky, dark brown, concentrated urine we call brine. One of the technologies that we're trying to develop for future missions is a brine processor so that we can get that last 10% or so water, even for future missions to Mars. But right now, you're right, we have to resupply that water. Some of that water comes up in the form of food. When they send the water up, they freeze dry some of it, but it still contains some water. And then we have resupply vehicles right now to the space station that bring up some water. For future missions, if we're going to send crews to Mars, that's about a 3-year round trip. We're going to have to take whatever we can't recover, 3 years worth of water with us.
All right, so no small task. You want to jump in, Jeff?
Well, I just wanted to there we go. I just wanted to mention a complementary technology area to the environmental control and life support system is that of in situ resource utilization. And so as we send rovers to Mars, as we learn about what's on the surface there, what sort of resources are there, is there water ice that we can access relatively easily on Mars or on the moon? We can start to think about how can we recover that and use it and to get our water that way so that we wouldn't have to take resupply if we'll try to close the loop, so as Robin pointed out, so that we get as much of that water that we put in back out for reuse. But the little bit we maybe can't recover, maybe we can get that from the surface. And ultimately, maybe we can get all of our water needs and our breathing oxygen needs from resources that are on the surface. So that's a whole nother technology area, kind of a complement to the life support technologies.
Okay. Great question to start it off. Who's next? Lori's pointing.
I'm on. Okay. My name is Michael Goodman. I'm at NASA Marshal, the Science Research Office. My question is for Nikki, and that is, what are example of the types of things you'll be manufacturing with the 3D printing in space? And can you give an example or tell me a little bit about the different protocols that will have to be utilized in microgravity and 3D printing versus what would be done here on Earth?
Sure, I'd be happy to. Let me set my mic. There we go. Okay, so the type of things that we'll be printing in the very beginning are going to be things that don't look terribly exciting to the layman, right? But we're super excited about. We're going to be doing tensile specimens, flexure, compression, range coupons. Those very first parts that we print, we have done a ton of detailed analysis on the ground to understand the material and mechanical properties for those parts, so that when we'll bring back those very first parts, the coupons, and we'll be able to compare them to the ground controls. And that's so we'll have publishable, conclusive data that shows if we do see any differences in microgravity and how we print. The best thing about additive manufacturing, which is the formal name for 3D printing, is that you can really create unusual, different than you can with traditional manufacturing parts in the way that you design. So design optimization is a key in understanding how the printing process works in microgravity. If it is different due to lack of convection or any other properties, will affect how we design, as well as the material characteristics. Now from there, we get to the really exciting part once we have that data. And we've started what I call a utilization catalog. And we have buckets and categories of things that we will be printing. Just like I mentioned with my colleagues here, I'm hoping to print some parts for them, as a matter of fact. But things like replacement parts for ECLS, filters, things for science payloads, such as sample containers. I just happened to bring one. We have a lot of, the more science we do, just like on the ground, we have a lot of ancillary hardware and disposable type things, syringes and containers. The idea is eventually we don't want to have to fly those up. We want the crew to be able to go over, push a button and say, yeah, I need 3 syringes, I need 3 sample containers, I need 4 tweezers. And also in actually how we build science payloads or parts of payloads. If you think about it, every single thing we launch, and this is so ingrained in us, we have to design it so that the structure survives launch loads, which usually means more mass and a different design than what we would do necessarily if we could make that part in microgravity. So we're having a lot of fun thinking of how we would design parts that we launch today. If we could produce them in microgravity, how would we design them differently? Also understanding the mechanical aspects of the additive manufacturing and the materials that we're printing with. The first material we're printing with is an ABS plastic, which is what Legos are made out of. So we've tested that in detail. So when we print a wrench, for example, it may not look exactly like the wrench you go get at your local supply store. It may be shorter and squatter. We have ways that we can take advantage of the mechanical properties and strength of that material. So to me, one of the most exciting parts about this, and I really encourage those high school students and college students out there today to consider a career path in this area, whether it's for space or on the ground, but how to design in a way that we can optimize the capabilities that additive manufacturing provides us. And for space travel, those implications are huge.
All right, thank you, Nikki.
I'll follow that up with another 3D printing question. So you mentioned a few advantages to 3D printing in zero gravity. Obviously, there are a few trouble spots, I guess, or things. Obviously, we wouldn't have a team of scientists working on it if it wasn't difficult. What are some of the advantages to printing in zero G, and do you have plans to leverage them, such as the fact that your Z-axis is now arbitrary?
Exactly. So these are things that we spend a lot of time postulating and hypothesizing. Again, I'll reiterate, it's a technology demo, so it's the unknown unknowns that I'm kind of most eager to see what we get. We do have on the 3D printer tech demo, we have 2 windows, and we'll have high-def cameras aimed at the prints while they're taking place. So we'll be watching live from the ground, and we'll be especially interested in seeing how the layer upon layer is being deposited. Things like the bead size, taking in the thermal properties in terms of making sure you have fans where they need. We have lack of convection. So these are things we've all thought out. And I did mention there's a couple areas we feel like it might help us. And then there are other areas that we are postulating but we'll need to watch. The most important thing, and what we've seen from the parabolic flights, is that the first layer that we lay on the print structure is really a critical juncture, and we see that on the ground as well. And we're very interested in seeing if that's any different in microgravity, and then the first layer that binds to the first bead that we have laid. That's going to be critical, and we'll see how it turns out. I will mention that all the items that we are going to print, we are loading on the we have a shareable nasa.gov website. We'll be loading all the files there, so anybody on the ground that wants to print the same parts on the ground can do so. And all of the data that we produce will be shareable. One thing we ran into with such things as materials and the different feedstocks and the different printers, there's a lot of data out there, but a lot of it is proprietary. A lot of these are commercial companies that have been working on these technologies for quite some time. So what we're doing will all be publishable, and I really encourage folks out there, we'll make sure those websites are available to participate along with us.
All right, who's coming up next? We got it. All right. First one from the right side of the room.
Good morning. I'm Lee Roop from the Huntsville Times, AL.com. Thanks for coming and doing this. So I'll follow up, I guess, to the ECLS system. Living in microgravity seems to be hard on the human body. We keep hearing about effects on vision, effects on bones, effects on more and more things. What kind of technology are you looking at now for long-term missions in space? How are we going to adapt our systems so our bodies can stand going up for as long as we're going to have to do it?
You're right. There's a lot of things we're learning about humans in space for long-duration missions, and we have a whole human research program at NASA to address those risks, and we're trying to retire all those risks on the space station as much as possible. You mentioned the intracranial pressure and the vision issues. The long-term effects of microgravity on the body. We have exercise equipment that we counteract those effects with. That exercise equipment on the space station is pretty large. For future missions where we want to take a spacecraft to Mars, we've got to reduce the mass of that equipment, make it as small as possible. We want, when the crews eventually arrive at the Mars surface, we want them to be able to get out of the spacecraft and be able to walk on the surface without being weak and have muscle atrophy. So that's really important. And we've got folks working on those technologies as well. As far as the ECLS system, we've learned some things. For example, the crew loses more calcium on orbit than they did on the ground. That's one of the issues that kind of surprised us. to be honest, and we had to adapt our ECLIS system. That calcium showed up in the urine and caused some hardware problems for us, and we had to adapt our system now, and we're working on ways to counteract that. So the longer we test these things on the space station, the more we learn. Ultimately, we want to get our Mars ECLIS system on the space station in about the next 5 years and test it for at least 2 or 3 years. So we're make sure it's reliable and it's ready to go when we need it for the next missions.
Okay. Who's next?
Hi. Hello. Hi, Jason Davis, Planetary Society, and you kind of just answered, Robin, my part of my question. I was going to ask you, how soon are you, how close are you to making a Mars-ready version of the ECLIS system? So again, you said about 5 years and then testing it for 2 years. And then my second question would be, how will you leverage some of the upcoming Orion flights, like EM2, going around the moon? Will you try to test some of that technology there, or will you try to just leverage normal technologies, bringing along all the water that's needed for those missions? Thanks.
Great. First of all, one more thing. Right now, our space station, I mentioned our water recycling system recycles about 90% of the water. We're working on technologies that will get that last 10%. On our air system for space station right now, we can recover about half of the oxygen from carbon dioxide. In other words, we recycle about 50% of the air. So we are working on technologies to further close that loop. We want to recover as much oxygen as possible so we don't have to bring up oxygen. So those are the kinds of things we want to work on in the next 5 years, hopefully, and get them up to space station and test those. How we're going to use the Orion mission? The Orion mission is designed for 30 days or less about, so we don't need to recycle as much on Orion. And it's also a small spacecraft, so we don't have some of our big water processor, for example, on an Orion. But we have some key technologies on Orion in our regenerative carbon dioxide removal that'll be tested. We have some critical environmental monitoring capabilities that'll be tested on an Orion. And so we are going to leverage the Orion to test some of those, some fire safety things that are new. For a small closed spacecraft, we're going to be testing on the Orion. So it's going to be things on space station for more of our long duration life support systems, things on Orion that go across any spacecraft we're going to have in our smaller spacecraft life support systems.
All right. We got another one up here.
I've got another question about the 3D printing.
You guys are popular.
Do you expect it to be more or less time efficient than the 3D printers on Earth? And is it going to be controlled by the ground or by the astronauts in the space station?
Yes, thank you for asking. So a lot of people ask us, what's the difference between this 3D printer and what you could buy off the ground? And the company we're working with, Made in Space, through the Small Business Innovation and Research Program, one of the first trades they did is, can we just go buy a printer off the ground? To be honest with you, a lot of the technical printing processes, the extrusion process is actually very analogous. But in terms of automation and being able to take advantage of remote operations, which we absolutely need to do, also to limit astronaut time, and as well as safety protocol, that was a couple of the key factors on why this printer has been specifically adapted for space. So the only thing the astronauts have to do on this printer is obviously install it, and then they have to remove the part from the print tray once it has been printed. Everything else, like I mentioned, we'll have live video watching the prints. We can turn the printer on and off. We can control the print, start the print, stop the print. We can do all of that from the ground, and we do have live video of the prints. As we continue on to Mars, I would like to take a minute to say this printer is a very first step to a lot larger suite of capabilities for sustainable exploration. So we have an in-space manufacturing initiative at NASA, and we include things like a recycler. For example, we get the question a lot that comes up, well, what if you still have to fly all the feedstock? Well, that's a very valid question. Feedstock is mass, and you're reliable on it at this point. So You do have to be able to recycle the parts. We've awarded 2 phase 1 SBIRs to small companies this past year who have already developed hardware where they are turning printed parts back into usable feedstock with multiple materials. And the real exciting day comes when Jeff had mentioned in situ resource, when we can use something like Martian regolith or lunar regolith to make the parts that we need, including such things as additive construction. We actually have another NASA project where we're working with large-scale printers, such as contour crafting, to be able to print things such as small habitat structures, radiation shielding, storage shelters, and landing pads. And we're testing regolith simulant from Mars and the Moon as our feedstock. So these are all capabilities that we'll need in conjunction. And as you mentioned, the remote operations is going to be a key aspect of that.
Okay. Who do we got next? Somebody grab the mic and jump in.
I had a question for Jose. I'm Alan Boyle with NBC News. I wanted to hear a little bit more about spheres and the next generation free-flying robots. What do you see as the schedule for using spheres and its successors on the space station?
Good question. So spheres, as is, has proven very durable for long-duration use. They've been up there for 8 years now, and they keep on ticking. They've been fixed. There have been some issues, but we've been able to go up and debug certain issues. So they're expected to actually work for a while yet, for another few years. But good question. We are looking, there are projects looking at what is the next version, what's the next free flyer going up to space station, and there's all kinds of ideas that are going into that to better enhance the free flyer's ability to assist the astronauts with various tasks, make all these tasks on ISS more automated. You know, there's a lot of things the astronauts do that that could be automated and save astronaut time, a very precious resource. So yeah, making them more renewable, making the propulsion renewable, these kind of things are being looked at for the next free flyer going up to space station. And there are projects looking at that right now.
And if I can just jump in real quick, you have a project up there right now that these spheres are actually using a piece of technology every single person in this room probably has either in their pocket or their hand right now, and that's smartphones.
Yeah, that's right. There's one project out of NASA Ames that's attaching smartphones to these spheres to be able to control the spheres from the ground. But what these smartphones actually do is turn these spheres into more robotic type application where again, we can control them from the ground, the astronaut can control them from the space station, and we can do more research in these collaborative type scenarios where the astronauts and robots can work hand in hand on all kinds of different tasks that will be needed for long duration spaceflight. So for example, environmental surveys, inventory control, camera movement. I mean, it'd be really great if operators on the ground were able to control a camera that can go anywhere in space station. So these are a lot of the tasks that we're looking at with spheres, and yeah, actually, there's actually this year. So that investigation was last year. Just this year, there's a new smartphone going up called Project Tango. It's a Google smartphone that just launched earlier this year, and the next test session for that is going to take place here in the next couple weeks. So be on the lookout for that online. We've got a Twitter account, nasa.gov/spheres. Also, we put a lot of information. And that's a really cool smartphone Google developed. And it's got a Kinect-like sensor that gives it an ability to map its environment in 3D. It generates a point cloud map of its environment. So then it could navigate throughout all of ISS without being limited. And it can do this using the special Kinect-like, like I said, a Kinect-like sensor together with a camera to do vision-based navigation. Because currently, the spheres are limited to the small volume inside the GEM module of ISS. Using 5 beacons, it locates itself within this particular area. But using vision-based navigation, it can navigate across ISS as would be needed for assistive type robots for the astronauts.
All right, very cool evolution. Next one right here, and then I think someone will get him next. So you right now.
I'm Frank Mooring with Aviation Week for Richard. The scan is radio-based, programmable radio. Are you doing work with lasercom, programmable lasercom for planetary exploration to get more bandwidth?
Certainly, as was mentioned, optical communications uses a laser beam as a medium of transmission, as opposed to the software-defined radios that we're operating are radio frequency or electromagnetic-based. But NASA is doing a number of things in optical communications. In fact, on Space Station, there's an optical payload entitled Optical Payload for Lasercom Studies, or OPALS. Now that's sort of scratching the surface of what Lasercom can do. So it's a laser onboard space station that communicates directly to a ground station on the Earth. There's a relay satellite also being developed that does optical communications, the Lasercom relay satellite or relay demonstration. So this will give us infrastructure in space so that when low Earth orbit satellites, which are optical terminal based, can relay their data back to Earth. And the bandwidth question, the data rate question, where we're doing hundreds of megabits today over RF, and maybe your cable system does 20 or 30 megabits to your desktop, RF will get us hundreds of megabits, multi-hundreds. Optical communication systems will get us thousands of megabits. It'll be an order of magnitude more. And there's a second optical terminal being considered for Space Station, which not only will give us optical communications direct to ground, but it'll also give us that low Earth orbit relay satellite. And as Nikki mentioned earlier, that we can only investigate on station, will give us the low Earth orbit satellite to use with that relay satellite. So those are all being developed at this time and should be deployed within the next 5 years. The radios for those systems will be programmable radios as well.
There's one other piece of, I might add on, it's the deep space optical comm. So in Space Technology Mission Directorate, which I represent, I have the happy experience of being able to work with all of these people here and 100 more doing the different technologies needed for space exploration. We have the laser communication relay demonstration project, which was mentioned. That's from in Earth orbit. But then we also have a deep space optical comm, looking at the unique features of communicating over very long distances, Mars and beyond, and all the particular problems that presents in terms of the rate that bodies are moving with respect to each other and how you acquire the signal and transmit the data. And so we've actually offered that technology. It's one of a suite of technologies that we're making available to people who are proposing for the next Discovery mission. So NASA is saying, here are some technologies we're developing. If you want to use these in your architecture for your Discovery mission concept, we'll continue developing these technologies and provide them, actually. So lots going on in optical comm.
I have one more thing to add, Dan. Sorry. There's also an additional system that's being investigated that combines the RF attributes of a system and the optical parts of a system. And when you mentioned the reprogrammable radio, the radios will be configured to operate waveforms that I mentioned earlier, either over RF or optical. And the idea of combining the systems is try to reduce mass on these systems, especially when they go to deep space, that the same antenna, the same aperture that's used to send electromagnetic signals can have this laser or a telescope integrated with it to conduct the optical communications with the same aperture. So that's more of a technology project underway now.
All right, thanks guys. I think we're gonna head back up this way again.
I'm Evan Coy from Grissom High School, and then another question for Robin about ECLIS, and well, not necessarily for ECLIS, but for more so life support in general, based on Jeff's comment on the possibility of water being on Mars, and for future life support for the possibility of using nuclear fission if there is water on Mars to create more oxygen, like nuclear submarines would.
Wow, we need to recruit you, so leave your name afterwards.
Stick around for an application.
You've got some great ideas, yeah. Definitely, as Jeff mentioned, our in situ resource utilization folks are looking at what kinds of resources we can use from Mars. Water is a great example, where we might build a habitat. Would there be water available that we could use for the ecosystem? Also, nuclear power is also a technology area that we're working on that will be very important when we get to the surface of Mars, so we have power to run all our habitats and all our things there. And in addition, as you might know, you probably do, Mars has a carbon dioxide, mostly atmosphere. So that's a great resource for us once we get to Mars to take that carbon dioxide and just extract the oxygen from it. And so we can use that for the crew rather than having to electrolyze water into hydrogen and oxygen right now, which is what we do to create the oxygen for the crew. So that's another advantage of we can use on the surface of Mars.
So we have a demonstration that's actually going to Mars on the Mars 2020 rover. It's the next generation rover, kind of like the one that we put on the surface of Mars 2 years ago. And it will do what Robin said. It will suck in the carbon dioxide atmosphere on Mars and produce oxygen. So it'll be an actual demonstration on Mars of taking the resources we find there and turning it into something we can either breathe or use as a rocket propellant to get us home.
Very exciting.
Hello, everyone. My name is Jennifer Lopez from Huffington Post. Thank you so much for telling us about your work. It all sounds incredible and exciting. I've two questions. First for Jose, if you can just tell us a little bit more about the Zero Robotics program, the competition with middle and high school students. And then also for Nikki, I just wanted to see if you can talk a little bit more about the materials. It was interesting when you mentioned the ABS. So just curious if you're able to divulge a bit more about what's in the pipeline, or if there's anything to use with PLA or any other materials. Thank you.
Zero Robotics is actually one of our exciting investigations and programs that we work with on spheres. And it's very much like the first robotics program, if you've ever heard of that, where high school students get to form teams and program the spheres and get to operate that on the space station. So it's very exciting. There's a website up where students can communicate and get involved. This happens every year with both middle school and high school students. And they form teams, they sign up, and they have a very good interactive environment online where they can program the spheres for the first time. They're learning how to program, they're learning for the first time how to program a computer. And they have a very interactive environment online where they can do that. And then at the conclusion of the event, watch their technology, their code run on the space station live, where we have a televised event, and the astronauts, in some cases, narrate the whole competition, where the students are programming the spheres to navigate and control against the game, where, for example, they might program the spheres to go around an asteroid, to man asteroids, or to repel an asteroid from destroying the Earth, and these kind of games where they get to have fun programming the spheres, and then watch the real thing on the space station. So very exciting, very great way of reaching out to the next generation of engineers and scientists, and getting that integrated with real technology happening on the space station. So very exciting. We have a lot of fun supporting it every year. From NASA Ames, we do a lot of the operations, a lot of the integration. And then MIT so far has been the key people involved with leading the effort and getting all the students together. And a lot of the educators as well. There's educators across the country that organize the schools into teams, and as well as the curriculum involved. There's a lot of things we teach the students how to do for the first time. So it's a great educational endeavor, and I'd advise anybody to take a look online.
And regarding materials, obviously that is extremely fundamental to this work, and we have spent a lot of time with these discussions. From the start, I'll talk about the technology demonstration, as I mentioned, uses ABS. The next generation printer, which is already under development, we've already taken a lot of the lessons learned in designing the technology demonstration and applied those to the next iteration. The next printer will have a larger build volume. It will use additional materials. It will be even more autonomous. And the type of materials at this point that we're kind of narrowing down on include Ultem 9085, which is used a lot today. Many of you might be familiar. It's a very, very strong plastic. It's got very great flammability ratings. FAA has used it quite a bit for things like airline seats. And we also use it since early shuttle days for a lot of our EVA tools. Another material we're very interested in is PEEK. So we're doing a lot of trades on those two for the next facility. Now the question comes up a lot, okay, plastics, what about metals? And that's where I think it gets a lot of fun too, because the metals technologies for in-space applications are a lot more challenging, quite frankly, than the plastics. We try to approach this from an applications perspective. What do I need to make? What customers do I have? And how that part, as I mentioned, may not look like what we're flying now. It may not be that metal wrench. So where are the areas where I know we'll need metals at some point, and where are the areas that we can focus on stronger plastics? Another area is carbon-reinforced plastics. They're even using that in some of the propulsion components. We call that the for-space area. I work in space, and we have for-space, and we share all our materials data, obviously. So the question becomes, if we're going to progress to metals, and what are the types of technologies we can use for those as well, and things like structures, or when you talk about going external in space and you look at the environmental aspects, metals obviously are superior there. So we've actually done an independent assessment with Wohlers Institute. If you're interested in additive manufacturing, I highly recommend looking at the Wohlers report, which he puts out every year. He does an extensive survey. And so we've looked at all the existing kind of known metals technologies out there, and then also some of the new novel technologies. Another reason I'm really excited about this work is this is something that's going to continue to evolve and at a rapid pace, I believe, for ground-based technologies. It's a disruptive technology, and there's definitely a commercial arena for it. And so we're working closely with academia and industry and other government entities such as DoD as these technologies evolve on how to take what is evolving and adapt it for microgravity. And that helps a lot in terms of schedule, but also, quite frankly, in terms of cost, working together as this community. So we've developed this materials and community that's interested in these discussions, and that's kind of where we're at currently with the plastics, the Ultim and the Peak as a next step. ABS is already used for quite a few things on orbit as well, a lot of the ancillary hardware I mentioned, as well as some of the CubeSat structures that have been launched, deployed from station or ABS. But we'll continue asking these questions and kind of evolving. As we collect that data from the in-space test, I mentioned we'll have that shareable database. We are publishing it for the ground controls and for what we do in space. Also, if I may take the liberty, since we talked about challenges and student involvement, I did want to mention we also have the first Future Engineers 3D Printing in Space Challenge. We just kicked it off through a Space Act agreement between NASA and the American Society of Mechanical Engineers. It's open to K through 12 through December 15th. The grand prize I want to mention is to design a part that the crew can use on orbit. We say a crew tool, but that can include medical hardware, daily usage type items, payload parts, and of course handheld tools. The winning student will actually, the part they design will be printed on the printer in space while they watch live from Mission Control, which I think is pretty amazing. And there are some other very exciting prizes, such as 3D printers for schools and things like that. So sorry, but I wanted to take the liberty to mention it's so important that we get student involvement because as much as I want to go to Mars, I'm quite frankly probably too old. It's going to be one of you guys. And I want to make sure we have that next generation excited and ready to go.
All right, thank you, Nikki. And since we're running out of time, I don't want to neglect our social media followers, so I think Shannon's standing by with at least one or two questions. And again, just for everybody in here, if we don't get to your question today, these guys are going to be sticking around after the show, so you can hunt them down and ask them your question, and they will answer.
Okay, so this one's coming to us from Twitter, and the question is, how many people can currently live aboard the ISS, and has that capacity ever been reached?
Eclipse.
Okay. Right now we have the ability for 6 crew to live permanently on ISS. We have had up to 9 with crew rotations. A new crew comes up, and before the existing crew leaves, we have had 9 for a short period of time. We could probably support more. That's what that's our current rotation though.
All right, cool question. And next one, Shannon.
Okay, and this question is also from Twitter. For the 3D printer, are we looking at a way to recycle and reuse the material so that old parts can be remade into new parts?
Absolutely. So I'm pretty tough on our guys about if we have replacement parts, and also, as I mentioned, for our feedstock, It's a tough argument to sell to headquarters, hey, let me fly this printer, but I'm also going to fly 50 pounds of backup feedstock and replacement parts. So actually many of our components for the printer, the print tray itself is 3D printed, as well as the extruder casing is a replacement part that we can 3D print on the printer. So I think it's kind of a cool do loop when you start to think about if we can print a new printer, print replacement parts for a printer, and that's exactly where we're heading. But that first fundamental goal, obviously, is to take existing materials on space stations, such as we use a ton of volume for packing materials, foams and plastic bags, and for launch packing. So if we can take those sorts of materials and recycle those into a usable feedstock, and that is something that we're working on through our SBIR program that I mentioned earlier, as well as the one we awarded this past year to 2 companies to take the parts that we've printed. We're looking at ABS, Ultim, and Peak for those as well, and turn those back into usable feedstock. Of course, we have interesting material studies to continue from there on how many times can you recycle, and do you start to see degradation, and when do you see degradation. So like I said, every thread we pull, there's a lot of exciting questions that we're working.
All right, and I just want to mention real quick, everyone following on social media or with iPads or Android, we have a new app launching this week. It's called ISS Research Explorer. You can actually learn about the thousands of experiments that have taken place on board station, the hundreds taking place right now. And again, it's ISS Research Explorer. It's coming out this week. So we're just about out of time. I think we only have about 4 minutes left or so. So I want to pose one final question to everyone up here. Just give your closing thoughts. And really, it's on the importance of the International Space Station for taking us to Mars. So when we have boots on the ground and people are looking back at planet Earth from millions of miles away, what do you think the station's legacy will have been to get us there?
Well, I think the legacy of the station in getting us into deep space will be providing that test bed to really wring out the technologies. It's top level. Getting to Mars is about getting there. It's about landing there, which is a pretty complicated thing. Actually, Mars has just enough atmosphere to be annoying, some people think. It's about living there. We're going to set up shop on Mars, and then about getting home. So get there, land there, live there, leave there. And the technologies we need to do that, which will sustain us over months and years in deep space, can be tested out on the space station. It provides the premier laboratory, ideal laboratory, and really the only laboratory for determining some of the effects the space environment will have on the technologies we need to take humans into deep space. So that'll be the legacy in my view.
And Robin?
I agree with Jeff. That's so important. We've got 10 years right now before the end of space station, and seems like maybe a long time, but it's not when you are thinking about all the work we still need to do using space station. In addition to the technologies, the legacy of the space station is the international partnership that we've built that will hopefully continue as we go do future missions with our international partners, all the great benefits to humanity that have come out of the space station, the research, even the water recycling system has spun off into ground-based systems that are being used for disaster relief here on Earth. So all of those things, in addition to the technology, are going to be important.
I think Spheres can contribute to some of that legacy in such that Spheres is actually one of the fewer science payloads that's been in continuous operation off and on for about 8 years now. Mm-hmm. And we've learned a lot about that experience, how to write procedures, how to build teams, how to support that kind of payload over a long duration, which is needed for long duration spaceflight. And then also in the area of robotics, I think there's a lot Spheres has to say about researching, well, how do humans and robots work with each other? How do you optimize that relationship and that team such that robots and humans can work together and automate a lot of the tasks that the humans don't always have to do? Mm-hmm. So very, very important for long-duration space travel where robots are just a critical application.
And Rich and Nikki, I need to ask you to go quick.
Sure. No, the legacy that I see for space station is really the long-term presence of humans in space and getting to such a point where it's almost routine to go that several hundred miles to space station and back, that we have the confidence and we've overcome the challenges to go further out.
So I'm Southern, but I can talk fast. You know the credit card commercials, the bottom line at the end where they say it's priceless? it's priceless. There's no other way we can test in a microgravity environment that's isolated to live and work, operate on a daily basis. That's what station's about.
All right, and thanks to all of you for joining me. Thanks to everyone here in our audience. Again, enjoy the rest of the tech forum. Come track these guys down if you have any additional questions. International Space Station up there since 1998, going to be there for at least 10 more years. Very exciting time for humanity in space. And as always, if you want to learn more about the stuff we've been talking about or anything else about the station, you can go to our website at nasa.gov/station. Thank you for joining us today.